Okay, I like this problem, a good speaker interference problem. So pause the video and read the question. Okay, so we've got these two speakers playing the same oscillator, they're running on the same audio oscillator. So we assume they're doing sine or cosine waves. I'm assuming cosine waves. They're spitting out sound. Initially they were right together, but then we've moved A over to the left here. So now there's some distance apart. And we want in part A, the girl here to be able to hear nothing. We want these two to interfere destructively and cancel out. Okay, so let's assume that they're both putting out cosine waves here. We want those two waves to cancel out. So let's say the green here is what B is doing. I want to scoot A over enough so that it completely cancels out B. Well, to do that, we have to scoot it by half a wavelength. Remember, a full wavelength is from crest to crest. A half a wavelength is from crest to the next trough. So if I take A and scoot it half a wavelength, then all the crests from B will be troughs on A and so forth, and everything. Remember, waves add as vectors. They add, we call it the principle of superposition. They just add together. Well, these will completely cancel out. This is how noise canceling headphones work. Noise canceling headphones listen to the environment and they hear this sound, and then they also produce a second signal. There are little speakers in there and they produce a signal that's the opposite of what they're hearing, and they'll cancel that out. Okay, so we want A to be half a wavelength. So we got to find the wavelength. Well, remember V equals lambda F. V is the speed of sound, our wave speed here. In air, that's about 344 meters per second. Our frequency, we were told, was 730 hertz. So the wavelength here is 0.47 meters. We wanted the distance between these two to be half a wavelength, so we just take half of that, 0.235 meters, roughly. Okay, part B, we want to now keep moving A, and now we want A and B, the two speakers, to interfere constructively. No, that's part C. We want the next time. We're going to keep moving A over. So as we move it a little further, she'll start to hear stuff. At one point, she'll be able to hear really well. And then as we keep moving A over, the sound will disappear again. Well, that would be 1.5 wavelengths away. So here I took cosine and I scooted it by half a wavelength for regular cosine. Remember, the wavelength for regular cosine is 2 pi, so half would be pi. So if I did 1.5 wavelengths, so 3 pi, oh, I wrote 3 pi. Again, we would cancel out. The green and the red cancel out. What if I moved one of them a full wavelength? Instead of an odd number of half wavelengths, an even number of half wavelengths. If I moved 2 pi, oh look, they completely line up. So in part C, we want to move it so that they interfere constructively. This question's a little ambiguous. They're producing constructive interference anytime they're not completely canceling out. What this means is constructive interference the best possible way. Where do the waves overlap so that she would hear stuff the loudest? And that would be when their difference is any integer number of wavelengths. So the smallest distance would be 1 wavelength.